Hey everybody, Mr. Piercy here, and in this video what we're going to be taking a look at is how to find the surface area of pyramids and cones. Now, surface areas of pyramids and cones are kind of similar to surface areas of prisms and cylinders, meaning that you can find the areas of the individual parts and add them together, but there's also formulas that we use specific to prisms and cylinders that we can use to find the surface area of any of those shapes. So first, let's take a look at the parts. Just like just like prisms, pyramids are classified by whatever shape their base is. So the one on the far left, depending on what type of quadrilateral it is, might be a square pyramid or a rectangular pyramid, depending on what type of quadrilateral that we have. But a pyramid is basically a polyhedron made up of you know different polygons, but the base is going to be some kind of polygon where it could be a triangle all the way up to however many number of sides that you want. Typically, it's not going to go past, say, like, I don't know, 7 or 8 sides realistically for the stuff that we'll be doing in class. The lateral faces are always going to be triangles of some kind. So we have the base and we have the triangular lateral faces. The vertex of the pyramid is where the lateral faces come together. A regular pyramid is going to, anytime they say it's a regular pyramid, that implies that the base, whatever the base is a regular polygon of some kind. Um, so the pyramid that's kind of more in the middle of your screen, that one is a regular hexagonal pyramid, meaning that the base is a regular hexagon. Slant height is going to be the height of the lateral face. Since it's the height of the lateral face, it's also often referred to as the lateral height of the figure. Here we have some definitions that we need for cones. A cone is just basically it's kind of like the cylinder's version of a pyramid. It's has a base that's a cylinder. I'm sorry, a base that's a circle. The lateral area, instead of being a mess of triangles that make up the lateral faces, it's not a face because it's not a polygon, but rather it's actually going to be a sector of a circle that we kind of wrap the curving piece of the sector around the circular base, and then everything kind of tapers together up in the vertex. The vertex of the cone is where the uh, lateral part of the cone kind of tapers together to a point. Uh, a right cone is simply going to be a cone. That's most commonly what we think of when we think of cones. It's where the vertex is going to be directly above the center of the circle. So the segment that contains the vertex and the center of the circle would be perpendicular to the base. And the lateral surface, again, like I explained a second ago, that is essentially a sector of a circle that would go around the uh, circular base. So this right here, the arc of the sector would be equal to the circumference of whatever the circular base is. And that S right here, whatever this, here, let me pick a different color to emphasize what I'm pointing out here. So let's go red. This would be the radius of said circle, but if you notice we're using S here because that's the slant height of the cone itself. So take the time that you need to copy down the definitions, and if you have questions about anything, make sure you write them down now so when we see each other or you message me, you can ask whatever questions that you have. But here in example one, all we're going to be doing is looking to see how do you find the area of each lateral face. Not together, but what is the area of one of those triangular faces of this particular pyramid. So it tells you it's a regular square pyramid. That's kind of redundant in my opinion, and if they're going to say it's a regular square pyramid, they can just say it's a square pyramid because square implies that it's a regular polygon as a base. But I'm getting off on a side note there. So we want to find the area of the triangular face. Now, sometimes the slant height is given to you, sometimes it's not given to you. Uh, Generally, there's going to be some kind of information given to you in the problem that you can at least figure it out. So let's look here. Essentially what they're doing is they're taking the height of the pyramid, the apothem of the square, and the slant height itself, and they're kind of forming a right triangle that they're looking at down here. So here we're going to use the Pythagorean theorem to figure out what the slant height is between what those pieces are. So we're only looking at half of the base, so that would essentially be, oh hey, look, I got an email from a museum. All right, great. Moving on. Here we're looking at the height of the pyramid, or the longer leg of the triangle that we see here is 97. The shorter leg of the right triangle is 45. So we're going to just substitute those into the Pythagorean theorem and simplify them and see what we get. And I don't know why my cursor's hanging out over that 97, but simplifying here, the square root of 11,434 does not have any perfect square factors, so we can't simplify that. If I left it as a radical number, it would be left as the square root of 11,434. We're going to go ahead and take the square root of that number, so we get about 107, just under 107. So that would be the lateral height of the pyramid. So now we can use that lateral height we can use to find the area of one of the lateral faces. So 1/2 times the base times the height, or in this case the lateral height, will give me 1/2 times 90 times that 106.9 number, which works out to be just over or just under 4112 square centimeters. So 4111.845 square centimeters as an approximate number. So now moving on, this is the equation that we use for the surface area of a regular pyramid. Now, of course, and it doesn't really need to be a regular pyramid, but these are generally the ones that you're going to see the most of. Actually, no, let me take that back. It really does need to be the surface. This is only going to be working for a regular pyramid, because if it's not, if the triangular faces are different sizes, we won't be able to use this. But where does this equation come from? It says the surface area is equal to the area of the base plus 1/2 times the perimeter of the base multiplied by the lateral height. Well, down here on the left, the lower left, it's just the general net of a square pyramid. So each side is, I'm just calling it S, and the lateral height, I'm just calling that L. Well, if I substitute those things into the equation, we're going to say the surface area is equal to side squared plus 4 of the triangles, which would be 4 times 1/2 times the base times the height. Well, the 4 and the 1/2, that simplifies to be 2. So it gives us S squared plus 2SL. Well, 2S is half of the overall perimeter, because the perimeter of the base is 4S. So 2S is half of that. So that's where the 1/2 P comes from. And of course, the B, the capital B, that's just the area of whatever the base happens to be. So that's how we wind up with the surface area is equal to the base plus half of the perimeter times the lateral height. Now, of course, you could always just add the 5 faces up. You could find the area of the 4 triangles and then add the square to it at the bottom. But we will be using the equation as we work these problems out. So here's the first one that we're working with. We have a regular hexagonal pyramid. Now here I do need to emphasize the fact that it is regular, so we can use that formula. And first thing I want to know is, well, what's the area of the base? What is that regular hexagon shape going to be? Now again, regular hexagons, are easy to work with because we can use rules for special right triangles with them. So we're essentially just kind of looking at, let me pick another color here. Essentially, we're just kind of looking at this kind of triangle here, that 30, 60, 90 triangle, where uh, the hypotenuse is 8, so the short leg would be 4, and the height of the triangle, and therefore the apothem of the hexagon, is just 4 radical 3. So we take that information and we substitute it into or we'll use that to find the area of the hexagon. But I do need the perimeter. So the perimeter, I have 6 sides that are 8 inches long, so that gives me a perimeter of 48. So here we get an area of 96 radical 3 square inches. And we'll leave it as a radical number because more often than not, in an academic setting, we will be looking at exact answers as opposed to approximate answers. So that 96 radical 3, that is the area of the base. So taking the equation that we have, the base plus 1/2 perimeter times the lateral height, substituting gives us 96 radical 3 plus 1/2 times the perimeter, 48, and the lateral height of 18. Now the 18, we didn't have to figure that out. That was just given to us. So simplifying here, that gives us 96 radical 3 plus 432 inches squared. That would be the exact perimeter, or I'm sorry, not the exact perimeter, but the exact surface area. Remember, 96 radical 3 and 432 are not like terms, so we can't actually combine those through addition. That's where we would stop for our exact answer. The approximate answer is just under 600 at 598.277. So that's the approximate area of the hexagonal pyramid that we see in this example. Well, now we're going to be moving on to take a look at cones. Cones, kind of like cylinders, are actually fairly easy to work with when we're finding surface area because the base is always the same. It's always a circle. So since the base is a circle, we substitute pi r squared for the capital B. And on the left where it says 1/2 c, well, that capital C is the circumference. So if I say half of the circumference, half of 2 pi r, I wind up with pi times r, and times the lateral height, just like it was in a pyramid. So pi r squared plus pi rl is the surface area equation that we'll use for cylinders. So now let's go ahead and work one out. So here I have a fairly straightforward cone, right cone, where the radius is 3, the slant height is 5, and so substituting those values into the surface area formula for a cone gives me pi times 3 squared plus pi times 3 times 5. So simplifying, I get 9 squared and 15. Those are like terms because it's essentially just a coefficient multiplied to a variable like 9x plus 15x. We can combine those. In this case, we'd get 24 pi meters squared. That is the exact area. That's where we would stop for the exact answer. For the approximate answer, multiply with pi, and we get about 75.4 meters squared. And there's the essentially how we work the equation for surface areas of a cone. So at this point here, guys, go ahead and pause the video, work out these two problems for the pyramid and the cone that you see, and when you're done, go ahead and come back and hit play. Let's check our answers and see how you did. But for now, pause the video, work these problems out, and come back when you're ready. Okay, so hopefully we have some answers that we can, make some sense of. But for the first example, the pyramid, we have a square pyramid, and it's asking us to simply find the area of each lateral face. So what is the area of each of those triangles that make up the sides? Well, again, it's just pi, 1/2 times the base times the height. Well, in this case, the base, the overall base of the pyramid that we're looking at, or the overall base of the triangle here is 20. And so the lateral height is given to you, the slant height is given to you to be 30. So those are what we substitute for the base and the height of the triangle. So 300 millimeters squared. Well, now we want to know what is the overall surface area. So I'm going to, now you could multiply that by 4 and then just add the square base to it, the 400 millimeters squared there. But I'm going to go ahead and just use the equation that was given to us. Uh, the surface area of the pyramid is the area of the base plus half of the perimeter times the lateral height. So s squared for the base, 1 half times 4 times s times l, because the perimeter is just 4 times the number of sides because it's just a square. Again, the perimeter will change depending on whatever the base is. So simplifying, 1 half of 4 is just 2. Substitute the 20 for the s and the 30 for the height or the lateral height. And simplifying gives us the area of the base to be 400. The area of the lateral faces is 1200. So together it's 1600 millimeters squared. And the last example that you guys are asked to work out is just find the surface area of the cone. It does say round your answer to 2 decimal places, but I really didn't pay attention to that. I gave my exact answer and rounded to 3 decimal places like AP Math asks me to. So taking the slant height and the radius that we have here, we're going to say surface area is pi r squared plus pi r l. Substitute 6 for the radius and 10 for the slant height. And simplifying gives me 36 pi plus 60 pi. Those are like terms, so together the exact area would be 96 pi feet squared, and the approximate area would be about 301.6. That's really gonna kind of wrap things up here. There's not too much really to talk about. Just like other problems that we've seen with surface area of prisms and cylinders, we can work the equations backwards. I could give you the surface area and ask you to find the slant height or ask you to find a particular variable for the area of the base. Um, or I could ask you to find what's the radius of the cone or the height of the cone, things like that. But otherwise, there's really not much else to talk about for surface area of pyramids and cones. If you have any questions about anything you've seen in the video, or you want to talk in any greater detail about something that I maybe could have explained a little bit better or that you didn't quite understand while watching the video, by all means, let me know, and I'll be happy to help you out. But until next time, ladies and gentlemen, thanks for watching and take care.